In this video, I will be explaining logistic growth and Euler's method. So first, let's review logistic growth. Logistic growth is mainly different from exponential growth because of the fact that there are limited resources. So while an exponential growth graph will keep increasing, a logistic growth graph will flatten out near its carrying capacity, which is shown on the graphs to the right. The carrying capacity is the maximum population size that the environment can support. And to do logistic growth problems successfully, you will need to know two equations. P is equal to K over 1 plus AE to the negative RT, and the derivative dP over dt is equal to RP times 1 minus P over K, where K is the carrying capacity, R is the rate, T is the time, P is population as a function of time, and A is found by doing the carrying capacity minus the initial population all over the initial population. So as you can see on this P of T graph, as time goes on, the population size will slowly start to flatten out near its carrying capacity. So from this, we can see that the limit as t goes to infinity of P of T is always going to be equal to the carrying capacity. And this is a good limit to have memorized for logistic growth problems. You should also know that dP over dt is at its maximum at half of the carrying capacity. So basically it's saying at k over 2, the population is going to be growing the fastest. Now let's review Euler's method. So we know that Euler's method is used when a differential equation cannot be solved through standard techniques, such as separation. The idea behind Euler's method is to use the concept of local linearity to join multiple small line segments so that they make up an approximation of the actual curve. And generally, the approximation gets less accurate the further away you get from the initial value. So that is also shown on the curve. And you're going to need two things in order to use Euler's method. You're going to need the initial point, and you're going to need the step size, or the change in x. So looking at number 1 on the worksheet, it says, suppose the population of fish in a lake grows according to dP over dt is equal to 3p minus 0.002 p squared, where p is the number of fish at time t in years. Part A asks you to find the limit as t goes to infinity of dP over dt. So looking at a P of T graph, we know that as time goes on, the population will slowly reach and flatten out at its carrying capacity, where the carrying capacity is the maximum amount that the population can grow to. Therefore, once the population reaches its carrying capacity, it's not going to grow after that. So we know that the limit as t goes to infinity of dP over dt, or the rate of population growth, is going to be equal to 0. Part B asks us to find the limit as t goes to infinity of P of T if P of 0 is equal to 100. Is the solution increasing or decreasing? So we know from a few slides back that the limit as t goes to infinity of P of T is equal to k. And in order to find k, we can use the dP dt formula we're given and rearrange it into this order, and whatever is in the denominator here is going to be equal to k. So we're given 3p minus 0.002 p squared, and in order to rearrange it to this, we have to pull out a 3p, and we get 3p times 1 minus p over 1500. So we know that k is equal to 1500, and that the limit as t goes to infinity of p of t is going to be equal to k, which is 1500. And in order to find if the solution is increasing or decreasing, we have to find if dP over dt is positive or negative. We know this from Calc AB. If dP over dt is positive, the graph is increasing. If it's negative, it's decreasing. And to find that, we have to plug in the initial condition we're given into dP dt. So when we plug in P of 0 is equal to 100 into dP over dt, where you plug in 100 for P, you get that dP over dt is greater than 0, so therefore the graph is increasing. So part C is basically the same as part B, just with a different initial condition. So it's still asking us to find the limit as t goes to infinity of P of t, and to see if the solution is increasing or decreasing. And here's where most people commonly get confused. They think that if there's a different initial condition, then the limit as t goes to infinity of P of t is going to be different somehow. But this is not true, since the carrying capacity is going to stay the same no matter what initial condition. So this will not change, and the answer is the same as in part B. The limit as t goes to infinity of P of t is equal to 1500. However, if the solution is increasing or decreasing might change. So we still need to check using our initial condition, plugging it into dp over dt. We still need to check if it's positive or negative. In this case, we get that it's still positive and the graph is still increasing. And just like before, we plug in 1500 for p into dp over dt. So part D asks how many fish are in the lake when the population of fish is growing the fastest. And we also know this, that from a few slides ago, dp over dt is at its maximum at half of the carrying capacity. And so part D is actually a very common question you'll get in logistic growth problems when you see that they'll ask you for some population value when the population is growing the fastest, and immediately you should know that that's k over 2. So in this case, that's 1500 over 2, which is 750 fish. And don't forget to use units and label because there might be points for that, and those are easy points you can get. So number 2 says, suppose a population of cheetahs grows according to the logistic differential equation dp over dt is equal to 3p minus 0.01 p squared. Which of the following statements is true? So the first statement is the limit as t goes to infinity of p of t is equal to 300. So we know by now that this limit is equal to the carrying capacity. Therefore, 300 must be the carrying capacity. And in order to check if this is true or not, we have to rearrange dp over dt to get it into the form we like, where it's 1 minus p over k inside the brackets. So when we rearrange this by taking out the 3p, we get 3p times 1 minus p over 300. And so we know that k is equal to 300, so this statement is true. The second statement is the growth rate of the cheetah population is greatest at p equals 1500. So we just did a problem like this in number 1, it was part D, and we know that the population is growing the fastest at k over 2. So we know that k is equal to 300, and if we divide that by 2, we get 150, which is not 1500. So this must be false. So statement 3 says if p is greater than 130, the cheetah population is increasing. So we know that in order to find if the graph is increasing at a particular solution, we have to plug in that solution into dp over dt and find if it's negative or positive. In this case, I plugged in a few different numbers that were greater than 130 to check this. So the first thing I did was plug in 140, where I got that dp over dt is greater than 0, so therefore the graph must be increasing. And at this point, some people may stop and just put that this statement is true, since at 140 it's increasing, and they might assume that after that it must be increasing as well. But you want to be careful and you want to plug in a few different points. And so I plugged in a value that was a lot greater than 130. I plugged in 1000, and I got that it was less than 0. dp of dt is less than 0. So this statement is false. And these problems, these types of questions are easy, but you want to make sure that you don't lose these easy points on not plugging in a few different numbers and really checking your answer. So make sure that you check your answer. So moving on to number 3. It says a population of animals is modeled by a function p that satisfies the logistic differential equation dp over dt is equal to 0.02p times 100 minus p. And part A asks if p of 0 is equal to 25, solve for p of t. And in order to solve for p of t, we're going to need 3 things. We're going to need the carrying capacity, A, and the rate. And we can find two of these things without even needing this initial condition. So all we have to do is rearrange this to get it into this form where we know where R and K is. In this form, we know that K is equal to 100, but we don't know exactly what R is. So we need to get it into this form where it's equal to RP times 1 minus P over K. So in order to rearrange it into this form, I just took out the 100 from the parentheses, and you get 2P times 1 minus P over 100. So R is equal to 2 and K is equal to 100. And now we use the initial condition to find A, which is K minus P naught over P naught, which is 100 minus 25 over 25, which is 3. And so now we have solved for PT. So parts B and C are very simple. Using part A, you know P of T is equal to 100 over 1 plus 3e to the negative 2t. It asks you to find P of 4, and then it asks you to find T when P is equal to 70. In both cases, in part B, I used the I use my calculator, and in part C, I simplified it algebraically. You can use either way depending on what kind of quiz you're taking or what kind of problem you're doing. So for part B, I got 100, and for part C, t is equal to negative ln of 1/7 over 2. So moving on from logistic growth to an Euler's method problem. In this one, we're given our initial condition, f of 2 is equal to 5, and we're given our step size and how many steps, 4 step sizes of 0.5, to approximate the value of f of 4. The only thing that's different about this Euler's method problem from standard Euler's method problems is that we have a table this time with x, f prime of x, and f of x values. So in order to make a tangent line for the initial condition 2, 5, we're going to need the slope at this point, and this is where the table comes in. We know that x equals 2, our slope, or f prime of x, is 0.2. So using this, we can use point slope form, or really any form, to create a tangent line. And then, of course, we all know how to do Euler's method. We just plug our next step size into this to find our next y, and then to find our next slope, we know that x equals 2.5, so our slope must be 0.4 from the table. So basically, that's the only different thing about this problem, is that we have a table. Other than that, this is a regular Euler's method problem, and we finally get that f of 4 is about 6. So number 5 is basically a standard Euler's method problem, but it's different from number 4 because it only gives you the step size, not the number of steps. And in the same way, number 6, as you'll see, gives you how many steps, but not the size. So basically, this is pretty easy to find. All you have to know is where you're starting and where you want to get to. And so we're starting at 0, we want to get to 0.6, and we know we have a step size of 0.2. So divide that, do 0.6 divided by 0.2, and you get 3, so there must be 3 steps of 0.2. And in both 5 and 6, I have used a table, as you can see. This might be a useful computation method for some people. It's just organized and neat. So I have x, y, m, and then the tangent line equation. But of course, after 3 steps, once I get to 0.6, I won't need m or the equation anymore, so I just cross that out. And so approximating using Euler's method, we get that f of 0.6 is about 1.808. And the same with number 6. It's basically the same problem as number 5, except this time you're given that you have 5 steps, but you're not given of what size. So in order to find this, again, you're going to need your starting point and where you want to get to. So we have x equals 2, and we want to get to the point where x equals 3. So that's a difference of 1. And we know we need 5 steps to get there, so 1 divided by 5, our step size is going to be 1/5, or 0.2. And that's going to be 5 steps of 0.2. So we have 5 steps in this table, with the 6th step being 3, where we want to get to. So again, just go through your normal Euler's method calculations, and you're going to get that f of 3 is about 0.944. And that's the end of the worksheet. So thanks for listening, and hope this video helped.